Okay, so 11.7 deals with quite a bit of graphing. So we'll be dealing with basically all different kinds of three-dimensional equations that produce surfaces that are, well, we call them quadric. It's kind of a fancier name for all these quadratic terms. So everything's usually going to be involving quadratic, terms for x and for y, or even z occasionally. Before we start talking about the shapes that you need to memorize, we'll just start with an example. And we'll talk about what you can do to kind of create the shapes. Like if you don't know, after we go through some of these, where they come from, this is how you can create all the graphs. So let's say we have z equals x squared plus y squared. Okay, so it's a little different than the other three-dimensional graphs we've done because now we actually have all three variables. Before we had two of them, and we would just extrude along the axis that was absent. So here, let's see. If we treat z as the dependent, you can see that z is going to be greater or equal than what? If you think of it like a domain or a range type thing. 0, yeah, because we got two squares, right? So here's our xyz plane. And now what we can do is create something we call traces, which is essentially involve just choosing z values. Like for instance, if I choose 0, that's not going to be very interesting because we're just going to get a point here. But if I did something like, let's say z equals 1, now the equation turns into 1 equals x squared plus y squared, which is the equation of a what? Okay, so if I go up 1 unit, where z is 1, now essentially I have a unit circle kind of centered around that position. Does that make sense? Okay. Yes, and if I increase z, like another convenient value would be, let's say we go all the way up to 4, right? Now I get the equation that 4 equals x squared plus y squared. So now if I go up to a height of 4, now I have a circle that has a radius of 2. And essentially you can do this over and over. And what you get is what we call a surface. This is actually a paraboloid, which we'll talk more about later, but that's your first surface. Okay, and most of these, so if you want to make it prettier, okay, that's what we're talking about. Okay, but the idea here is that when you don't know the shape, or if you need to know what's going on at a certain height or a certain z value, you can just plug in some particular values, and you can see what shape you have on that plane. Okay. Let's see. Did we talk about? We'll talk more about that next unit. Okay. So before actually, this will be good. Let's just go through the shapes, and then I'll use Maple to show you some pretty pictures that'll do certainly a better job than I can. But okay, so let's start with this. Some general shapes. Okay, so we're talking about 6 basic shapes here. The first one looks something like this. X squared over a squared plus y squared over b squared plus z squared over c squared equal to 1. Okay? Yeah, please. Careful. You all right?
Yeah.
Okay. Thank you. Which looks suspiciously like what? An ellipse, right? I mean, if you ignore one of the terms, it's just an ellipse. And actually, that's what's going to happen. If you do traces, all the traces are ellipses. Okay, the equation may not start out in this form, but you can transform it into something that looks like this, and the graph is exactly what you think it would be. In the x direction, you would go out A. In the y direction, you go out B. And in the z direction, you go up and down C. And so you just draw an ellipse. Easiest way to do it is probably draw 3 ellipses, one on the xy plane, so there's this one on the xz plane, and what am I missing? Oh, I didn't do the xy plane. I did zy, xz, and now if I do xy, okay, not the world's greatest picture. It's supposed to look kind of like a football. Think about, it's like a sphere, but it's not the same radius in each direction. Maybe I can retry that. That's a little better. Okay, so here are the 3 ellipses, and together you get a surface that looks kind of like Stewie Griffin's head, if you're into Family Guy. Okay. So that's the first one. It is called, I don't know if, did we say it officially? This is called an ellipsoid. The next one will be anything that can be written as z squared equals x squared over a squared plus y squared over b squared. So it's actually almost like the first example. The only difference is that now z can also be squared. So instead of having the domain or the z values be only greater or equal to 0, we could have negative values as well. Okay, so if you kind of think about this shape, we're basically going to have a mirror image down here, but it won't be a parabola anymore. Okay, this is going to create what we call an elliptic cone. Okay, now because z is squared, we will straighten out that curve and I mean, it's exactly something like this. Okay, so this is an elliptic cone. And again, probably the easiest way to graph this, when it's in this format anyway, if you look at the xy plane or parallel to the xy plane, when z equals 0, you actually get these lines. But as soon as we increase z to 1 or anything like that, now we actually get ellipses again, or circles, depending on whether a or b are the same. Okay, so you can kind of see those here. So as we increase z from 0 to 1, we get more ellipses, and those are the traces that we're graphing here. Okay. Questions? How is it what? It's got a z squared as opposed to just z. Oh, how can he distinguish then? I see. There's no constant term here. You see how for the elliptic or the ellipsoid, okay, you have another term besides just the three equations, or the three terms for z, x, and y. Does that make sense? Okay, so whenever you have that, you'll be able to set it equal to 1, and then you'll get an ellipsoid. Whereas here, you can't set it equal to 1. If anything, you can set it equal to 0, but, you know, that's how you can differentiate. Okay? And that's good, that you're looking for ways to differentiate between the different shapes. Because they are going to look kind of similar, but there are going to be some differences that will help you guys remember what's what. Okay, so the next one looks something like this. X squared over a squared plus y squared over b squared. And now here's one of those differences. Minus z squared over c squared equals 1. Okay. And this is going to create what we call a hyperboloid of one sheet. Okay, and now, I mean, a few different ways that you can do it. If you think about the xy plane, so again, plugging in some values for z, you're still going to get ellipses no matter what. But even if z is 0 now, you don't have just a point here. Now you actually have some kind of ellipse already in the xy plane. Does that make sense? Okay, and then now as you increase z, whether it's positive or negative, you just increase the radius of the ellipse. So your traces look something like this. Both directions. So basically the surface looks something like this. Okay, so this is a hyperboloid of one sheet because it's all one surface that's kind of connected. And because you could actually also, these are all ellipses here, but if you look at, let's say, the x, z or yz plane, or planes that are parallel to those, now you can see the other traces, which are hyperbolas. Okay, so that's a hyperbola on the yz plane, and we can't see it, but there's one here on the xz plane as well. Okay, so that's where it gets the name from. And again, you can distinguish between the three shapes so far because here we have a negative z term, and probably the easiest way to remember this is that then the hyperboloid would be centered around the z-axis because that's the one that has that negative sign. Okay, so if I were to alternate, let's say I had a negative x term and everything else was positive, this would be the exact same shape, but now this would be along the x-axis. Does that make sense? Okay, so that's a pretty easy way to remember how to graph these. Sorry, I didn't write this down, so. Okay. The next one. Is a hyperboloid of two sheets. And the equation looks very similar to this one, except now instead of one negative term we have two. So let's say we have z squared over c squared, and then everything else is negative. Okay, and again, if you think traces, if you plug in some constants for z, so we get either the xy plane or planes that are parallel to it, you're going to get an ellipse but there's going to be a disconnect because for certain values of z, you wouldn't actually get an equation that you can graph. So that's why we get the two sheets here. So the graph's going to look something like this. So now you get a hyperboloid of two sheets. And again, you have hyperbolas depending on which way you look. If we have x, y, and z again in the yz plane and xz plane direction, we have hyperbolas for our traces. You can see here's one of those. But now if you're parallel to the xy plane, so if you slice the surface parallel to the xy plane, you see how we get ellipses, right? So there's all your ellipses. What's that? Yeah. Yeah. Okay. So that's 1, 2, 3, 4. Two more. We've already done this one, so this is actually like the first one that we did. So we're just going to write it down now. This is an elliptic paraboloid. Sometimes I'll drop the elliptic part and just call it a paraboloid, but it looks like the first equation. We'll have z equal to, and then two square terms. So x squared over a squared plus y squared over b squared. And I think it was pretty clear here that this is like the first example. Let's see. In the xy direction, how did we create it? We did ellipses, right? When we first did the example. So there's the ellipse, or one of them. And of course, there's every time you take a slice parallel to the xy plane, there's another one. So those are the traces in the xy direction, parallel to the xy plane. But if you look at the yz and xz planes, what shapes do you get there? So if you were to slice parallel to the yz plane, what would we get? A parabola, which is why we call it an elliptic paraboloid. So I'll use a different color. Here's one of those parabolas. Okay, and certainly if you come out a little more, you get another one. If you go back, you get more. Okay, but that's where all the shapes come from. Okay? All right. So this next one is a little difficult to draw, but I'll do my best. This next one, yeah. So, why, were the other ones kind of hard to draw? They're kind of hard to draw. What's that? They look like circles. It takes practice. Believe it or not, mine have gotten better over the years. This is about as good as it gets for me.
Pretty good.
Hyperbolic paraboloid. Paraboloid. Oh, thank you. The last one was called an elliptic paraboloid. Okay, so pretty much the only other combination of pluses and minuses with what we've been looking at is this one, where we have z equal to, now instead of two square terms where we add them together, now we have the difference, so maybe like y squared over b squared minus x squared over a squared. Okay. So if, all right, let me try to, so let's look at the xy plane first. If I do z equals 0, when you plug z equals 0 into this equation, you get essentially that x squared over a constant equals y squared over a constant, which is actually just two lines intersecting at the origin. So like if we're looking top down, this is kind of what we would see if we're looking from top down to onto the xy plane. Okay? If we go up to z equals 1, well, now we get what? Plug z equals 1 in here, and what do we get? A hyperbola. But, let's see. Y squared would be positive, right? So, if we're looking top down, y is left and right. So the hyperbola would actually be opening in the y direction. Does that make sense? But now if I go down, this is what creates this very interesting shape. If I plug in -1, the only thing that happens is that the terms switch signs, right? So it's still a hyperbola, but now it opens in the x direction. So now it's going to open forward and backward. Okay. Okay. So now here's what basically happens. Basically. All right. Here we go. Yeah, I mean.
I totally see it.
Here's the x-axis. Here's the z-axis. And here's the y-axis. Okay. If you're having a hard time seeing what's going on, well, that's okay. But I will this will make sense. Here's what we like to call it. We have an even fancier name for this. It's called a horse saddle.
What?
A horse saddle. Or Pringle.
Pringle.
How is that a Pringle?
Well, a Pringle does not extend infinitely. You have to use your imagination here. Okay? That would be the ultimate Pringle, but if you imagine, here's the basic idea. Let's pretend that you're standing right here, okay? Can you guys pretend that you're this little dot here? If you were to come out, can you guys see what direction you'd go, up or down? You'd go down. This here, maybe this will help.
Yes.
Is there another side?
There isn't, well, we can't see it, it's covered up. So if you go forwards and backwards, you will be traveling downhill. Does that make sense?
Yeah.
If you go left or right, you're going to be traveling uphill. Does that make sense? I'll show you some pictures here in a minute, but if you imagine a Pringle, I mean, really, that's the shape that we're talking about.
It's really not, though.
No, it totally is.
No, because a Pringle doesn't do this in the center. Does that, like...
If you went that direction, would you be going down? So is that point like the top
Wow.
of the...
Yeah, me neither. I don't even know if I'm gonna try.
Can you show me like, hey, what's the other side of it?
It looks exactly like this.
Okay, so like, if I do like...
Can we get some Play-Doh?
Hold on.
Use a meter stick.
No. The meter sticks will not help us now. Okay. So you know what? Here, let me do a couple of examples so you get the idea for some rough sketches. Yes.
So like at the ends there, like on like the y-axis.
Right here.
Does it just keep getting bigger and bigger?
It does. Yes.
So it doesn't like repeat. It won't.
No. So like this just keeps going up. It starts to kind of, if you think of a horse saddle, right?
Yeah.
You climb up a little bit, but then it kind of levels off. But it does continue to increase. Okay. I will. Yes, I'm getting there. I'm just trying to do this in a manner so I don't have to keep switching back and forth between maple and then trying some. Let's just see what we can do on our own first. Use your imaginations, right? And then maple will save us all. Okay. So, some techniques. For rough sketches. Whoops, apparently I can't spell today. If we have x squared over 9 plus y squared over 16 plus z squared over 9 equals 1. If you can recognize what shape this is, then you can probably sketch it pretty quickly. Anybody know what it is? It is an ellipsoid. Because everything is squared and we have it equal to 1. It looks like the ellipse equation, right? So for a rough sketch, how do you find x and z intercepts? Well, and y intercepts. You just plug in 0 for all the other ones, right? What are your x-intercepts going to be? 3 and negative 3. Y? And then 3, negative 3. Oh, no. I screwed that up. Everybody makes mistakes, Eddie. I said y, just didn't put it in the right spot. Okay, so x is 3 and negative 3, right? This time stop me if I'm messing up. Y was 4 and negative 4 for the intercepts. And z was also 3 and negative 3. So you draw your 6 intercepts and ignore, like, I don't know, you want to start on the YZ plane. So there's this point. Or there's one ellipse. If you go XZ direction now, there's that one. And XY would be kind of something like this. I mean, that's not awful, I guess. As long as you guys understand what shape you have, that's really the most crucial piece of this. Okay? Any questions on how we got that? No? A lot of them? Enough so that you know what you're going on, or you know what's going on. Because, I mean, eventually we're going to be integrating some of these things and doing all these cool things with it. And if you can't, I guess it's not the end of the world. If you can't understand what shape you have in front of you, you could probably still do the calculations right. But a lot of times if you have a vague idea of what's going on and what's overlapping what, then you should be in good shape. Okay.
If we can't draw it, can we just list out the x-intercepts and stuff?
Yeah, whatever you got to do. Yeah. Okay, another one. So let's say we have 4x squared minus y squared plus 4z squared equals 4. Okay, so what are we looking for here? Well, we have, yeah, if we divide everything by 4, and if we want to, I suppose we could put the over 1, right? This looks kind of like the last example, but now we have one negative term, so this makes it a, yes, one negative sign, one sheet. Now, along what axis? Well, the one that we did, the general example was we had z as the negative term, right? This one has y as the negative term, so we're going to be centered around the y-axis. Okay, so if you make y equal to 0, so if you do y equals 0, you get an ellipse on the xz plane, right? You get x squared over, well, actually it's a circle this time. Just a unit circle. So you could just draw x and z intercepts at 1, negative 1. You draw a little unit circle there. There's one trace, and this is one sheet, so all we're going to do is just kind of do something like that. And actually, from my perspective, you wouldn't be able to see that. This is probably better. You don't have to shade, but sometimes, you know. So there's your hyperboloid of one sheet. Okay, so again, you don't really, these are just rough sketches. So if you have some information that helps you get started, like we knew it's one sheet, we know that there's a unit circle on the xz plane, and as we radiate outwards towards positive and negative y, they just increase, and you know what the general shape looks like, then you're good to go. Okay? Does this kind of make sense? It's going to take some time. I understand that. Now let me show you some pictures. And now I will stop recording because I don't know. Well, maybe. Can I record my laptop while this is recording? Let's find out. Ah, I don't even have the right adapter. You know what? Let me stop this and make sure this saves.